noise with hardware counters on HPC systems. As you can see, this is a corporate work between the Technical University of Darmstadt and the Forschungszentrum Jülich. You can see that Markus, Alexander, and me and Felix are from the Technical University of Darmstadt, while Nur and Bernd are from the Forschungszentrum Jülich. To be precise, we actually presented part of this work at the Pro Tools workshop during the SC22 in Dallas last year. And what you will see here is basically a bit more extended version and a few more aspects about the future work. So let's start with the motivation. So as you know, the performance and complexity of HPC systems is becoming more and more complex, and the applications are becoming also more complex. So it's basically very important to identify performance bottleneck at an early stage, and this is basically our motivation. So what you usually do is that you use performance modeling. This has quite a long research history, and it's actually very good to predict the scaling behavior of an application, and thus allows you to identify performance bottleneck at an early stage. But the problem is that if you perform, or the performance models basically depend on the measurements, and on noisy environments, you basically have very much noise in the measurements. So you have strong variations in the measurements, and the measurements also become irreproducible and misleading. So you can think, if you use these measurements to generate performance models, the performance would basically deviate strongly from what the real behavior of the application is, right? So this is something we don't want. And what we actually want is a performance model that accurately describes the scaling behavior of the application. So let's look a bit more into this topic. So you can see here a graph. Don't worry about it right now. I will explain it in detail at the end, or near the end of the presentation. But what you can see is on the x-axis, you have the relative deviation for the mean, from the mean. And on the y-axis, you have, for example, here the time. And how you can think about it is that we had like repeated runs several times, and then you calculate the deviation from the mean. And the further away these values are, the more deviations there is actually. And you can see here two kinds of plots. You can see a blue one and an orange one here. And what is interesting is that the blue one actually is very short, as you can see here, while the orange one has quite some deviation. And this means that it's basically, so the metric, the time is basically, which is here on the y-axis, is strongly affected by noise. So you can think about, if you use this metric to generate performance models, you can see that there will be a lot of deviations, right? So what we thought of is, why don't we use hardware counters? Because hardware counters are basically little impacted by noise. And this is something you can see here also on the y-axis. So you have here the double precision operations. And very interesting to see here is that in the presence of noise or no noise, it's basically nearly the same. So they are nearly resilient to noise. And this was our motivation. But you see, the problem is on different systems, you basically have different hardware counters, and you also have a lot of them. And the question is, which hardware counter do you actually use to boost your performance models? So what you need to do is actually do like a large scale analysis on the system and see which counters are good for performance modeling and which are not. And this is basically exactly what we did. So we ran nearly 26,950 experiments on different systems and inspected the hardware counters to see which were suitable or not. What we did is that we looked into 5 different systems. From these 5 different systems, we had 4 different hardware architectures. So we had a few with IBM processors. We had also a few, we had 2 with Intel processors. We had also with AMD and ARM processors and so on. And we looked also into 3 applications. So we used these different architectures, different applications. And we injected noise into the system. Here's important that we injected the noise. It's not just the system noise, but we had a tool with which we could inject noise and not. And we had different resource configurations. So we varied the number of nodes on the different systems. And you can see this is quite a bunch, right? And to be like, to have more confidence in the results, we basically repeated the set up 5 times per configuration you see here. Okay, so what we ended up in total is that we could categorize the hardware counters into categories like good, bad, and okay counters. And we also provided a user guide which could help people who are working with performance modeling to select the right hardware counters. Now, in this presentation, I want to look into what you see here a bit more detailed. So we will start first with the analysis methodology. And as I told you, what we want basically, so the motivation is to see which hardware counters are resilient to noise and which are basically not so resilient. And what we did is first, we examined how the measurements of the same counters are when you repeat the measurements. So we repeated the measure several times and see how the counted values changed. Next, we exposed the hardware counters to different levels of noise to see basically the resilience of the hardware counters against the noise. And for that, we used a tool which is called Neugena. And you can think about it like a collection of benchmarks. And Neugena basically takes a pattern, and based on the pattern, the noise is generated. So as I said, we had like 5 repetitions, and here you can see, so in each repetition, we took a pattern. And here you can see one of these patterns. So what it just says, it's an input file for Neugena. So what it says is that repeat the noise for infinity, so till the job terminates. And while you are doing so, perform first 2 seconds of network noise, then do no noise for 2 seconds, then do memory noise for 2 seconds, and then again, please do no noise for 2 seconds. So you give Neugena this pattern and run it. And the important point here is that we run Neugena on the odd processors so that the application processes were running on the even one. And this way we could make sure that they are affected by this noise generation tool. Okay. Okay, so now that we generated basically all this data, you basically need a way to make it like to understand or interpret it in a right way, right? And this is why we came up with a metric to compare basically the different call paths of the different applications from the repeated experiments and so on. And what we ended up with is a relative deviation from the arithmetic mean. So if you remember, this was the figure a few slides ago. And all you do here is that you calculate the mean, which is V bar, and you subtract the sample. So you subtract VI from V bar from the mean and divide by the mean. You multiply it by 100 and you end up with a percentage value. Now, to be a bit more precise here, what we did is that we looked into the 8th application kernel, the P's MPI rank, the T's open MP thread, and the E's repetition. Okay, so you have like four loops. And what we did is that we calculated the mean over the repetitions. So you can see here the mean is basically calculated over the repetitions, and you'll end up with this value, V bar. And when you subtract from each of these repetitions, basically the value from this mean, you can end up with this metric. So it's somehow more linked for each application, but it's also globally visible since it's just a relative metric. And what we did so far, or what we did is that we counted this value for all counters on all systems in the presence and in the absence of noise. Okay, and this is basically the graph we just saw a few minutes ago, but I will explain it later in more detail. Now let's look into the applications we used. So as I mentioned, we had 3 applications. Here you can see them. They are Mini-FE, Lulish, and LAMPS, so they are all 3 well known. So Mini-FE is a mini app that mimics the finite element generation, assembly, and solution, and it solves basically an unconstructed grid problem, as usually encountered in many engineering applications. Now, Lulish solves the pseudo-blast problem, and it represents algorithms and programming styles like you typically encounter in scientific applications. So this was the motivation behind choosing these applications. We wanted applications which are well known and basically are also representative to what you usually use in HPC. Next, we also looked into LAMPS, which solves the classical molecular dynamics code. And here we in particular looked into the Leonard-Johnson potential. Now, for all applications you see here, we enabled OpenMP and MPI. So we had both OpenMP and MPI doing all the measurements. Okay, so you see where we're going, right? So next we're looking into the systems. And as you can see here, we have 5 systems. Their name is to the left. So we have the CM, ESB, Eureka, Zetchen, and Cyclops. The upper 3 ones, so the CM, ESB, and Eureka, are from the Forschungszentrum Jülich, while the lower one, Zetchen and Cyclops, are from the University of Oregon. Here again, many thanks for Samir Shani for providing us access to these systems. Now, looking into the first 2, you can see that they are both with Intel, so they have different technologies, of course. One is with the Intel Xeon Skylake, and the other one is with the Intel Xeon Cascade Lake. And you can see they're also of different sizes. So the CM cluster has 50 nodes, while the ESB cluster has 75. You can see that the CM cluster have 12 cores with 24 threads, while the ESB has 8 with 16. Regarding the network topology, both use InfiniBand, and they have also different RAM sizes. But you can see, so we wanted to pick basically 2 different systems, but with the same architecture. So this is why we had 2 Intel systems here. Next, our largest system in the study was Eureka, which had 480 nodes. And you can see we have 64 cores in total, 128 threads. So it's quite large, right? Here it is also InfiniBand and has also quite some RAM. The next 2 systems are quite small. So if you look into Jetson, it has only 12 nodes and it has 4 cores and 4 threads. So quite small. Cyclops, on the other hand, is with IBM Power 9. So Jetson, it was with ARM, and Cyclops is with IBM Power 9. You can see we have 20 cores with 80 threads. Okay, so these are the 5 systems we use. And as I said, we have 2 Intel systems, 1 AMD system, 1 ARM system, and 1 IBM Power 9. Okay, so out of everything I said so far, you can basically come up with different combinations. And this is the combination we came up with. You can see to the left the name of the applications. We have here MiniFE, you have here Lulesh, and here LAMPS. Then you can also see the system. We have here CM, ESB, Eureka, Zetchen, and Cyclops. So you have 5 every time. And here you can see basically the experimental configurations. With n, the number of nodes, you can see we picked them, for example, in MiniFE with the CM cluster, we took n equal to 1. Then we have p, which is the MPI ranks, equal to 1. Then we have t, which is the threads, equal to 12. And in the end, we have s, which is the problem size also as a function of the MPI ranks. So every time you pick up one of these, you end up with a configuration. You take the 2, you end up with a different one, and so on. Now, this is just for one cluster. You can do the same for the different clusters, and you can see you end up with quite a large number of combinations. This here was for MiniFE. Lulesh takes cubic nodes, and here you can see that we had also always a cubic number. And for LAMPS, we also tried to pick a different configuration. So we tried to diverse a bit so that we have different results, basically, which are a bit more representative. Now, you see out of these combinations, you end up with 26,950 experiment, as I mentioned. And now you actually needed a reasonable way to display all the results you obtained, right? And to be a bit more precise, for each counter, you have basically the task to display it for the 3 different applications, so 1,000 of different call paths, the different resource configuration, several iterations per setup, 5 different systems, and in the presence and absence of noise. So we have several counters, right? And what we thought of is that 5 different systems and several counters, we can just use distant plots for that, right? This is quite easy. So you'll have basically a plot for every system and so for every system and every counter. Because this was a bit more easier than like putting everything over each other. Now, the next point is that you have here these 4 points, or 5. You have these 3 different applications, call paths, the resource configurations, and iterations per setup. And what we thought of is that we can just use this relative metric, which I just described a few moments ago. And since it's a relative metric, you can just basically group all this information inside it. Now, we still wanted to know a bit more about the different call paths of the applications and so on. So what we thought of is that we play a bit with the intensity, so it's the alpha. But again, I will explain it just in a few moments. And so the call path, we basically play with the intensity to show the importance to the overall behavior. So the darker color on the plot is the more important this call path was to the total contribution to the counted values by a counter. Okay. And next, I said we have this presence and absence of noise. And if you remember, we had this green and orange plots. And this is what we did. We just used separate axes for each plot we generated. And finally, to compare the different counters, so since you're counting values, right, we scaled the plots to the peak occurrences of the maximum relative deviation. Okay. And now I said actually a lot about these plots, so maybe we just take a look into them and I'll explain them a bit more into detail. So here's one of an example you see. You can see on the x-axis, we have the relative deviation from the mean, which is in percent. On the y-axis, we have the name of the counter, which is here total instructions. And on the right, you can have, we have the system name, which is in this case Jetson. As I said, we have in the upper part without noise, so the blue part, and we have the lower part, which is in orange, which is with noise. So always up is without and low is with noise. So we try to extend a bit here the zero area, so you can see a bit more clearly that there's no deviations in case there is no. And as you can see, we have different shadings, and this is what I mentioned a few seconds ago about the alpha. Excuse me a bit. Exactly, this is what I said about the alpha, that the darker the color is, the more important the call path is. So let us go through, oh, sorry. Yeah, I think. Okay, so let us go through the description a bit more in detail. So I said the height of the distribution plots basically describes how often the corresponding deviation occurs. So as you can see, there are relative population distributions, and the more height region is, the more often this counted value or this deviation occurred, right? And as I promised, we tried to scale here with the peak occurrences, while you always will see this plot filled to the maximum. So we scale with the peak relative deviation for the call path. And what we also try to do is to filter out call paths which are not so important, so which did not contribute to more than 1% of the total counted value. Okay. Okay, so next we played with the intensity, as I said, and the intensity shows the importance of the region to the overall behavior. So you can see here two regions are quite clear, which you can see, and you can see the darker one is just more important. And we defined importance as the call path share to the total counted values. So the more this call path basically resulted in counted values, the more important it is, the darker it is. So larger values indicate parts of the application that just exhibit more behavior that describe the counter, okay? So the darker it is, the more basically this call path played a role in this counted value. Okay, so I said that we try to classify the counters into good, bad, and so on. So let's maybe start with the bad counters. Here are two examples on the left and on the right. On the left, you can see that, so this is how we define bad counters. You have this blue part, which is short, so short below 20%. So this counter has not so much deviations in case there is no noise. And once we injected the system with noise, you can see that we have quite some deviations. And this is basically how you can see that this counter is strongly affected by noise and is a bad counter. Now on the right, you can see a different example where the blue is already large and the orange also. So again, orange large means it's basically a bad counter. And the blue large basically means that we do not know why this counter is bad, but because there can be two reasons. There can be, for example, it's just the nature of the counter. For example, here it's the L3 load misses. So it's just the nature of the counter to basically have variations. It could be that the counter is just affected by system noise, or it could be that the counter just does not count correctly or something like implementations related. So, but in either way, we do not care. What we care about is that this counter is not suited for modeling, since it has large deviations, as you can see here. So these are two examples of the bad counters. Now let's look into good and okay counters. So good counters, as you probably guessed it, you have short regions here. you can see that it's below 20% for the blue, so it was similar as in the bad, but you can see here's the significant part. The orange, which is in the presence of noise, is also short, which means this counter is not affected by noise. And in this case, it's just the instruction issued, so it's the total instructions issued, which you see here on this axis, and you can see it's not affected by noise. Okay, so on the right, you have an example of an OK counter. And the counter is, so we said, okay, if it's robust to some extent to the noise. So again, you have a short blue part, which is good. And you, in the orange part, you can see the dark orange. Remember, dark means, or let's say a higher alpha means that they are more important. So you have the important call paths are below 20%, so nearly below 20%. And this is why we say that this counter is an OK counter. You can see that there's some stuff going on here, which is not the case here in the good counter. And this is how we tried to differentiate between them, especially since the important call path is just below 20%. Okay. Now, let's go into the results. But before going into the counters, let's look maybe first at the time. Again, this was our motivation. And here you can see the 5 systems. You have the CM, ESB, Eureka, Cyclops, and Jetson. On this axis, you have here the time. So we are looking here into how the time varies and to the relative deviations. And what you can see here is on the Intel systems, so the ESB and CM, you can see in the absence of noise, the deviation is quite small. So this is the blue part. And in the presence of noise, the deviation is quite large. So these systems are affected, let's say, strongly by noise. On Eureka, you can see that this is the case with and without injection. So this counter, so basically if you use these metrics for modeling, for performance modeling, in noisy environments, you will end up with bad results. Now, if you look into Cyclops, this is kind of interesting because Cyclops, I don't know if you pay attention to the system description a few slides ago, you could see that Cyclops just has a single node. And the interesting point here is that in the absence of noise, it's quite good on the system, but it's just a single node. So I don't know if you want really to call this a cluster. But here on the section, you can see that the deviation in time is also quite large. And again, this is also, you would also, if you use this metric, obtain bad performance models. And so having said that, you see that time is not always the best choice, exactly. And so this is why we wanted to look into the hardware counters, and let's now look into the results. Let's start with the obvious thing, the floating point operations. And as you probably all guessed it, the floating point operations are perfect. You can see that the double precision vector instructions, so here, exactly, I don't know, you can see it right here. They are basically very low, and you have also the double precision. So basically in every system, these values are very low, right? So these are counters which are quite good suited. So it's not only the floating point operations, but also the instructions. Okay. And next, let's look into a different category, which you would not probably have guessed straightforward, that they are also good counters. So what you can see here to the left are branch and cycle instructions. So you can see here the branch instructions issued. Remember, as we said, below 20% is actually a good counter. You can see especially here the store instructions are quite good. The total instructions are also good. Here also the branch mispredictions and so on. So also a few L1 level cache are good. And this was all on the Jetson cluster. And on the Cyclops cluster, you can see that you have also quite a few counters which are suited for performance modeling. Or let's say it a different way, we have a few counters which are basically not so affected by noise. Okay. Now let's look into not so good counters. Like we said previously, we called them OK counters. And you can see that we have here the L1, L2 instruction caches and then instruction cache miss. For example, here you can see it is affected by noise a bit, but not so much. So the dark orange basically is below 20%, and this is why we call them OK counters. on the ESP system. You can see few counters basically have some stuff going on here, but the important call paths are located in the part here below 20%, which is why you can argue that they are okay counters. On the Eureka, you have the same story. The importance, so you really need to zoom in to see the very dark color, but you can see here, for example, that the dark color here is basically focused below 20%. And in Cyclops, as you would expect, the values are quite small, which is very good because this means the system is not so much affected of these counters. But we know already that the system was also not so much affected by noise. On the intersystem to the right, you can see that they are also the same for these cars, also the instruction cars misses, axis, hits, and so on. They all have like the important call paths below 20%. And now maybe something very interesting is that the miss from one level, so when you look here at the L2 instruction cast miss, is basically related to the axis of the second level. So if you look into the L3 instruction cast axis, you can see some similar behavior between these two, right? And you can see the correlation. There's actually a correlation between the counters, which we wanted to look into maybe as a future work, but I will get to that later. Let's look also a bit into on the different system, also on OK counters. Here, especially on the CM cluster, you can also see that the maximum instruction completed here, the full CCY, or the maximum instructions issued here, are also with the important call path below 20% in the presence and absence of noise. Absence is blue, sorry, and presence is orange. So these counters are also quite good. We have some stuff going on here, but this is the call passes that are not so important, and this is why we would consider these counters also as okay counters, and they could also be used for performance modeling. Also here, the branch instructions and the load instructions, the total instruction especially. So total instructions and total instruction cycles seem to be quite good on both systems. And as I said, since you have some stuff going on here, you would just refer to these counters as okay counters. So they're not the best choice, but they are a good choice. Now let's look into bad counters. And as you can see here, we have the stars. You can see that in the absence of noise, the deviation is quite small. In the presence of noise, you can see how fast this deviation goes. Also for the important call paths, as you can see here, for this cycle state on any resources. So here the RES STL. And you can see that this dark orange continues. So this is basically a very bad counter. Also for the cycles where no instruction were completed or issued, which are here, you can also see the same story is true. On Eureka, on the total instructions, we also said that they are not so good. As you can see here, some deviations and so on. So this is how we try to classify these counters. Now, let's look into Cyclops, and this is quite interesting because, as you remembered, I said in the previous, or previously I said that Cyclops actually has not so much noise in time. So there are also some hardware counters which should not be used, like here, where you can see the deviations, which are quite large. And this is why we would not recommend to use them in performance modeling, especially because they have larger deviations at the time, right? So these are counters you should avoid if you are working with performance modeling. Now, in all these graphs, what you always see here, so if you look, for example, here into this counter, you can see that all three applications were basically grouped into a single plot, as I mentioned previously, with this relative metric we calculated. Now, it would be interesting to see what happens if you like split it up into three applications, right? And this is what we basically did here on the next slide. So we have here in the upper part the time, and you have here in the lower part the load instructions. And the interesting point is that we split this up into the three applications we have. So we have here lamps, we have here Ludesh, and we have here mini-FE. And what you can see here, they are all the same counter, so it's always the time. And you have here again the different systems. So if you look on into this figure, we just have the time and lamps in the CM cluster. And this figure, you would have just the time and Lulish also in the CM cluster, and so on. And the plots we obtained basically previously was by grouping a row basically here. Okay. So if you look into these figures, you see the motivation behind using different applications, because if you just use a single one, for example, here, you wouldn't see that the time would deviate a lot on the CM cluster, right? Or on the ASP cluster. But once you use Lulish, you can see completely different results. And this is why we thought we need to have more applications, and ideally we would have more than 3. But I mean, with the 3 we took, we ended up with 26,000 or nearly 27,000 experiments. And you could guess that adding just one would add like nearly 10,000 or 15,000 more experiments. And this is why we stick to 3, basically. You can see this is the same story is true for the hardware counters. So for the log instructions, while LAMPS looks quite good on all systems, you can see that once you use Lulish on the different systems, you obtain a completely different story, right? You obtain some deviations in the presence of noise, also some deviations on the absence of noise, as you can see here on Cyclops, which was not here. So we obtain quite some interesting results. As I promised, we tried to give a best user guide in the paper we wrote, and I just wanted to go very fast over them. So what we could say is that independent of the system, you could always rely on the floating point operations and the floating point instructions. And this is something we also saw a few slides ago, because they are basically the counters which have flow deviations, the presence and absence of noise. On the Intel systems, we saw that the instructions and cycles had strong deviations for the less important call paths, but small deviations for the important call paths. So the one which were basically darker in color. And this is why we said that these categories are basically good if you want to use them for performance modeling. The star and the reference cycles, on the other hand, were not so good because they had large deviation, especially also for the relevant call paths. And they were not so accurate. Next, we had also so remember, Intel was the CM and the EST cluster. For the AMD cluster, which is Eureka, which was the largest system, you see that the L2 caches are quite good, so the access and miss, because they had small deviations for the important call path. And bad were basically the branch instructions, because they had more deviations, but they are still good for modeling, or they had too much. They had still too much deviation to be used for modeling. Exactly. This is why we would also say that you should not use them. On the IBM system, so this was on the ARM system, which was Jetson, you can see that the instruction and cycles are quite good. And there was an exception to the total cycles because we had strong deviations in it. This was the Jetson cluster. And in the last one, which was the IBM Power 9 system, which was Cyclops, you could see that for most counters, you had probably less than 30% for the significant call paths. So you could basically use nearly all, except what I said later about the S-related caches and the branch, and here's the load instructions and so on. They had some deviations. To sum up, I tried to come up with a table, as you can see here. And as you can see, the floating points are the best ones. Double plus stands for the best ones. And for the remaining systems, you can see that the cycles and the instructions are not so bad. So I would say they could be used for performance modeling. On Eureka, they were not so good, but on the remaining systems, they were quite good. And on the different systems, we also had, for example, on the AMD, we would recommend the L1, L2 caches. So the hardware counters associated with these caches. On the Intel system, we would avoid them. And you can see that here are some aspects of some signs missing. And this is because we either did not have access to the L3 level cache, or there is simply no L3 cache. Okay, so let's conclude. So what we did so far is that we examined the noise resilience of the hardware counters on the 5 different systems. So it's the 4 different architectures we had here. We analyzed how it is the presence and the absence of noise, and with different applications, as I just mentioned in the presentation. What we saw so far was only the preset counters. We had also 18 selected native counters, but as they were not so interesting, I just skipped that. And we believe that you actually need to do a more extensive analysis to include all native events and to see how the native events basically relate to that. or how they are affected by noise. And this is also something for our future work. In general, you can say that most hardware counters are affected by noise, but still less in the runtime, which we have seen. There are a few exceptions. Remember Cyclops. Counters measuring the floating points and instructions are quite good on all systems. And the variability basically depends on the system architecture which is used. And we provide this guide to aid the performance develop or the people working with performance models to select the right hardware counters. Now, as a future work, we actually are currently working on a tool which we aim to deploy in the system, and you can just like let it run. And in our imagination, at the end, when it's completed, it just tells you which counters are good and which are bad. And we are currently working on that. Next thing is that we also are looking into the native counters. As I mentioned, there are quite a few native counters, much more than the preset. And we are looking how noise resilient these counters are. As I mentioned also, there's a correlation between the counters. We are also looking a bit more deeper into these aspects, how the counters correlate with each other. And we also want to identify the source of the noise. So let's see how far we get with that. We wanted to see, are the counters bad? Are the systems basically very noisy? Where does this noise come, which is basically affecting this counter to deviate so much? And this is one of our future objective, to be precise. And we have also joined forces with the PAPI developers who we are working currently with to inspect these aspects I mentioned previously. Okay, so I think that's it for my presentation. If you have any questions, please feel free to ask. I think we have still a few minutes.
So thank you for the interesting talk.